In the following, we'll discuss multivariate Gaussians, which are a generalization of Gaussian distributions to many random variables. So we'll introduce the multivariate Gaussian density, and as said, this is now then a distribution over many random variables instead of only one. And we'll discuss the geometry of multivariate Gaussians. So in particular, we'll illustrate this in two dimensions. And then we'll give the maximum likelihood solution for multivariate Gaussians. So yeah, so far we've only considered a single random variable and their distribution, and in particular the Gaussian. But this is, in machine learning, we have typically a high dimensional data. And so fortunately, the Gaussian has a straightforward generalization to many variables, so to multivariate random variables or to random vectors. And here's the definition of the multivariate Gaussian. So let P be a probability density defined as follows. So this density is now over a vector of states. So this is now a vector in a d-dimensional Euclidean space. So d dimensions. So X is a d-dimensional vector. And the distribution, so the multivariate Gaussian, is parametrized with a mean vector mu. So this is now a d-dimensional mean vector. And with a d times d matrix sigma. And we require that that sigma is positive definite. So that it's a positive definite covariance matrix. And this is pretty much the same as we had in the Gaussian over only one random variable, so sigma had to be positive, and the rule is now that the covariance matrix must be positive definite. So again, two parameters, mean and covariance essentially, and yeah, the mean vector, a d-dimensional vector, and the covariance, a d times d matrix, a positive definite matrix, and it has a very similar functional form as the one-dimensional Gaussian, so 1 over 2 pi times to the power of the dimensionality times the determinant of the covariance matrix and square root. And again, we have, so this is again the normalizer or normalizing factor. And again, we have the exponential function of a quadratic form. But now this quadratic form is a vector quadratic form. So we have the x vector, so our data, minus the mean vector, transposed times the inverse of sigma times x minus mu. So this is actually a rather straightforward generalization from one dimension to many dimensions. So in the one dimension we divide it by sigma. Here we have the inverse of sigma, and we have this vector quadratic form. So a very similar form as in the 1D case, and yeah, so this is the definition of the multivariate Gaussian. And so in 2D we can nicely plot this. So here this is a two-dimensional Gaussian or bivariate Gaussian. So you have one dimension here, another dimension here, and so Gaussian looks like this bell shape here. And often it's more convenient to look at it from bird's eye perspective. So if we look at this function from bird's eye perspective, then we would see something like this. So here yellow means high density and blue means low density. And if we look at this function from top, then it would look like something here. So the color indicates the height of the density, so to speak. So this is the definition of the multivariate Gaussian. So pretty similar form as in 1D. And so where's the probability now? So for one-dimensional distributions, we said that the probability density is essentially the area under the curve. So based on a certain set A, so the set an event A, and it's essentially pretty much the same story here. So consider a multivariate random variable. So and we call them a multivariate random variable or a random vector. We denote with bold-faced letters, so to indicate that these are many. And say we have d random variables. So we have d single-dimensional random variables, and we collect them into in a vector. Essentially, our multivariate random variable has d dimensions, and each dimension is essentially just a real valued random variable. Now, if we have a density for this random vector, so the density is actually just a function in d-dimensional space, so probability is very much as for single random variables. The probability is given by the volume under the density p of x. So this corresponds to the probability of events. So for any given event, so we have now d dimensions. So we have now the d-dimensional Euclidean space, and for any event which is a subset of the d-dimensional space, the integral under the function, so essentially the volume under the function graph, which is based on this set A, is essentially the probability of A. So the density, if you integrate the density over a set A, this should give the probability of A. So this is exactly the same story as in 1D. So to give an example, here we have again the Gaussian distribution from the previous slide. And for example, so consider a set, so the strangely shaped A, which is a subset of the two-dimensional Euclidean space. So this is just a subset. And if we integrate, if we look at the volume under the density based on this event, on this subset, this should be the probability of this A. So A is an event, and if we integrate the density over this event, over this subset, this should give the probability of A. And if we are following a frequentist notion of probability, this is essentially the frequency, how often does the two-dimensional random vector end up in this set here. So the integral of the probability density gives the probability, and this is the frequency, how often this random vector ends up in this set here. So pretty straightforward generalization from one-dimensional probability densities to higher dimensions. So again, integrating the density gives probability. So how do multivariate Gaussians look like? And so it's easiest to discuss this in 2D. So essentially, we can represent Gaussian PDFs by looking at the density contour lines, or here we are representing the log density contour lines. And generally in multivariate Gaussians, they take the form of ellipsoids. So in 2D, we have essentially that the equi probability density or log probability lines, the contour lines, they have elliptical form, so circles or ellipses. And now if we play with the mean vector, so like in the 1D Gaussian, the mean vector essentially determines the location and the mode of the PDF. So the mode is the maximum of the PDF, and so the PDF assumes its maximum at the mean vector, and by moving around the mean vector, so here, for example, this is 3 times the same Gaussian, so with the same covariance matrix, but with different mean vector. And essentially, by moving the mean vector, we can essentially just move around this this bell shape. So if we look at it from top, this bell shape, the equi contour lines. The equi density contour lines are these ellipses, and we essentially just can move around the Gaussian bell by changing the mean vector. So pretty much the same story as in 1D. So this is the role of the mean vector. What is the role of the covariance? So again, so the Gaussian contour lines, the density contour lines are ellipsoids. And so the form of the ellipsoids is very much controlled by sigma, so by the positive definite covariance matrix. And again, recall positive definite means that if we take sigma and we multiply it from left with a vector A, a transpose, and from the right with the same vector, this must always be non-negative. This must be for any vector from the d-dimensional space. So this is just a definition of a positive definite matrix. And now if we play around with, so if we now keep the mean fixed at 0, 0, if we now play with the covariance matrix, we observe the following phenomenon. So the elements in the diagonal essentially scale the variance in each dimension. So if we have only zeros in the off diagonals, and we play with the diagonal elements, so here's the Gaussian for where the covariance is the unit matrix, so only once in the diagonal. And we see that here the equidensity lines are essentially circles around the mean. If we now take the second diagonal element, so corresponding to the second dimension, we change it to 3, we see that the circles change into these ellipses. So like in this dimension, the circle gets extended to an ellipsoid, and essentially this is essentially the variance. So like here a variance of 3, while in this dimension we have a variance of 1. And vice versa, if we change again the second dimension back to 1, and we change the first dimension to 5, we see that we have a high variance now in the first dimension, and only unit variance in the second dimension. So this happens when the off diagonals, so the on diagonals are essentially like variance terms, and the off diagonals are essentially covariance terms. So if we play, if the off diagonals are all 0, then we see that these circles and these ellipses are essentially axis aligned. So it's these circles and ellipses are well aligned with the axis, and this happens when the off diagonal elements are 0. So if the off diagonal elements are non-zero, then these ellipses essentially become slanted. So here. Again, here in this example, we have a covariance where the off diagonals are 0, and we see this ellipse is axis aligned. And if we now change the off diagonals here, for example, to -0.5, then we see the ellipse gets slanted towards the left. And if we change it, for example, to something positive like 1, it gets slanted to the right. So the off diagonal elements, they are the covariances. And if they are not 0, if they're unequal 0, then this ellipses essentially become slanted. If they are all 0, the ellipses are axis aligned, like in this image. And if they are non-zero, then essentially these ellipses become slanted. And then interesting thing is, so if the off diagonals are non-zero, and therefore these ellipses are axis aligned, this is the same as assuming independence among the random variables. So if all the off-diagonal elements are 0, this is the same as assuming independence among the variables. And in this case, the multivariate Gaussian factorizes into a product of 1D Gaussians. So recall, so this is our multivariate Gaussian. And if the off-diagonal elements are all 0, then it factorizes into a product of 1D Gaussians. And the dth Gaussian, so here each of these factors is a one-dimensional Gaussian. Each of these one-dimensional Gaussian is just given by the dth element in the mean vector and the dth element in the diagonal of the covariance. So if all the off-diagonals are 0, then first of all, the ellipses are axis aligned. And we are actually assuming statistical independence among the dimensions, which means that the multivariate Gaussian is given by a product over a single dimensional Gaussians, and the product runs over all dimensions. So this is by definition statistical independence, and this is reflected in the graphs by axis aligned ellipsoids. And so here we represented this in 2D. But also in higher dimensions, Gaussians are ellipsoids. So figure a 3-dimensional Gaussian, this would be a 3-dimensional ellipsoid somehow oriented in space, and also in higher dimensions, Gaussians are given the equiprobability, density lines are given as ellipsoids. Okay, so this is describes the geometry of Gaussians. So we have the mean vector, which essentially moves around the center of these circles or ellipsoids, and the covariance essentially determines the shape. So if all the off-diagonals are 0, the shape is axis aligned, otherwise the shape is slanted. So can we say something about how we can actually find the shape? And there's an interesting connection to PCA, which we discussed, which Sibylle discussed recently. So again, so the off-diagonal entries, if they are non-zeros, then the ellipsoids are not axis aligned but slanted. And we can find this orientation by essentially applying a principal component analysis, or the singular value decomposition applied to our covariance sigma. And to this end, so let's take our covariance sigma, which parameterizes our Gaussian, and apply the SVD. And the SVD gives us 3 matrices, so the U matrix, the S matrix and the V matrix. And since sigma is positive definite, it's therefore also symmetric, and therefore U and V are essentially the same. And if we now take the ith column of U, this essentially is the principal component using the covariance. So when we discussed the PCA, principal component analysis, we applied the SVD to the empirical covariance of the data, and now we just applied to the covariance parameter of a Gaussian. And essentially it's pretty much the same story. And this the columns of our U matrix essentially give us the principal directions of these ellipsoids. And the diagonal entries of the S matrix, they give us essentially the variance along the principal components. So just as a small side note concerning notation, when we discussed SVD and or when Sibylle discussed SVD and PCA, she called this middle matrix sigma, which is standard notation for SVD. But in this lecture, we reserved sigma for the covariance of the Gaussian. So therefore, I use the symbol S here. So don't be confused. Well, in the SVD lecture, this was called sigma, but sigma is now the covariance of the Gaussian. So here we use S. So if we apply the SVD to our covariance, we get essentially the directions of the ellipsoids, and we get also the variance along these principal components. So we can draw this. So if we have like this Gaussian with a particular covariance sigma, we can now visualize the principal components. So we just need to take U1 times the square root of S11. So S11 is the variance along this direction, and the square root is the standard deviation. So this red line here, so this red vector is essentially this corresponds to this first principal component, and the second vector is essentially the second biggest principal component, so square root of S22 times the principal component vector U2. So just by applying SVD, we can actually we can figure out the orientation of the ellipses of the Gaussian. And this works with arbitrary high dimensions. So if we have a 100-dimensional Gaussian, we just need to apply the SVD to the covariance, and we find these principal directions which determine the orientation of our elliptical equidensity contour lines. So an interesting connection to PCA and Gaussian distributions. Yeah. So how does maximum likelihood now work for multivariate Gaussians? So we in the last section we derived the maximum likelihood solution for a one-dimensional Gaussian, and this was pretty intuitive. The maximum likelihood mean was just the average over the data set, and the maximum likelihood variance was essentially just the empirical variance over the data set. So very intuitive results for maximum likelihood solution. For the maximum likelihood solution for 1D Gaussians. And as said in the previous section, we can apply mean and bar from NumPy to do this. So these two functions in NumPy already do this for us. And it's pretty much the same story for multivariate Gaussians. So similar story for multivariate Gaussians. We essentially just need to take the mean vector of our data. So now our data is vectors, sampled vectors, and if we just take the mean of this vector, this gives us the maximum likelihood solution for multivariate Gaussians. So pretty much the same story in high dimensions. And for the variance, instead of computing variances, we need to compute the empirical covariance. So this is given by the function cof in NumPy, and this is given by vector xi minus the maximum likelihood solution mu hat times xi minus mu hat transposed. So this is essentially, this is a vector, and this is a row vector. So this gives you essentially a matrix, a rank 1 matrix, and you essentially just need to, so the outer product of the vector xi minus mu hat and xi minus mu hat. So this is the outer product and the rank 1 matrix, and you essentially just need to average these matrices over the whole data set, and this is the empirical covariance of your data set. So in PCA, we computed this and applied SVD to do principal component analysis. And here, this is in in the context of multivariate Gaussians, this is the maximum likelihood covariance. Yeah, so pretty much the same story, 1D Gaussian and multivariate Gaussians, sample average and sample covariance gives you the maximum likelihood parameters for multivariate Gaussians. So let's check this in empirically. So here I produced data, so 500 samples from a Gaussian, where I just set the parameters to 2.1 and 0.7 for the mean vector. So this is the true mean vector, and this is the covariance matrix, so 1 and 1.7 in the diagonal, and 0.63 in the off diagonals. And I just produced 500 samples from this Gaussian here, and by doing the maximum likelihood estimate, so just the average over these 500 samples gives the maximum likelihood estimate for the mean vector. And this gives here 2.14 versus 2.1 and 0.74 instead of 0.7. So this is pretty close. And for the empirical covariance, we also see that this is pretty close. So instead of 1, we get 0.92. Instead of 0.63, we get 0.56. And instead of 1.7, we get 1.55. And here we see the data, and so this this contour lines are essentially the maximum likelihood fit. So yeah, great. So this is how we do maximum likelihood with multivariate Gaussians. And this already concludes the section on multivariate Gaussians. So it's actually a pretty straightforward generalization of 1D Gaussians. It essentially just becomes high dimensional. So first of all, the functional form of the Gaussian density becomes the high dimensional correspondent. So we just get a different factor here, so 2 pi to the power of d. And we have the determinant of sigma instead of just sigma itself. And in the quadratic form, we have the inverse of sigma instead of 1 over sigma as in the 1D case. But still, it's just a quadratic form, but in higher dimensions, exponentiated and having a normalization factor. And like in 1D, the volume under the curve based on a certain event, so a subset of the Euclidean space, yields the probability of this event, so of this subset. And essentially in frequentist notion, this is the frequency, how often the random vector ends up in this bin, so in this high dimensional bin now. And so in frequentist notion, this would be the frequency, how often the random vector ends up in A. And we saw the geometry of multivariate Gaussians. So they are ellipsoids, so the equiprobability or equidensity contour lines, they are ellipsoids. And we saw how we actually can figure out the orientation of this ellipsoids essentially just by applying PCA, or actually the SVD, to the covariance matrix. And well, the principal components describe how the ellipsoid is oriented in space.